You guys saw the work energy theorem, correct? Now we are going to do the same thing but for a variable force. Okay. Now before we start with the actual derivation, see, kinetic energy was what? Half mv square, correct? Now remember, m is the mass, v is the velocity with which it's going. Now we are going to do differentiation of the kinetic energy. Okay, so differentiation is a rate of change, we can call it. Okay, meaning for a very small amount of time, what is the change in the kinetic energy? Okay, like for example, see, take an example of a cricket ball. Now the batsman hits the ball. For a very small change in time, there is a change in kinetic energy. So we represent this as dk by dt, meaning for a very small change in time dt, there is a change in kinetic energy dk. Okay, so dk by dt, that means we have to differentiate half mv square. So we get d by dt of half mv square. Now m is constant, half is constant, only the velocity changes, right? So what we get is half m into 2 times v into dv by dt. Now this is the way of doing a differentiation. You guys will learn that in the next video. So for now, so think of it this way: whenever you differentiate v square, we get 2v into dv by dt. Now 2 and 2 will get cancelled, so you end up with dk by dt is equal to mv into dv by dt. Now if you remember, what is the rate of change of velocity? Acceleration, correct? So we end up with dk by dt is equal to ma into v, right? So what is m into a? F. So we have dk by dt is equal to f into v, right? Okay. Now v, velocity, can also be written as rate of change of displacement, correct? So we have f into dx by dt. So we have dk by dt is equal to f into dx by dt. Now dt dt cancels, so we just end up with dk is equal to h into dx. Now why are we doing all these things? That's very important, right? We just differentiated. What is the point of doing all these things? See, what was work energy theorem? The change in the kinetic energy and the work done. We were relating that, right? So here also we are going to do the same thing. So dk is what? Change in kinetic energy. We have f, we have dx. X is what? Displacement. So when we integrate this, that means integration of dk from ki to kf is equal to f into integral of dx from xi to xf. Now ki is the initial kinetic energy, kf is the final kinetic energy, xi and xf initial displacement, final displacement. Okay, so here you get kf minus ki is equal to f into xf minus xi. So see, xf minus xi is nothing but the displacement, right? So what is force into displacement? That's nothing but the work done. So we have kf minus ki, that is the change in the kinetic energy, is equal to the work done. So what we conclude from this is, irrespective of whether it's a constant force or a variable force, the work energy theorem always holds good. Okay, so in this, let me just tell you what we have done. We took kinetic energy, we differentiated that, meaning we are looking at the change in the kinetic energy. That's why we differentiated. So when we differentiated, you get the change in kinetic energy in terms of force and change in displacement. Okay, so that's where you got dk is equal to f into dx. Now when you integrate that, you are going to get the change in kinetic energy, that is kf minus ki is equal to w. Okay, so work energy theorem holds good for constant force as well as variable force.